this presentation, we're going to introduce the moisture condition evaluation in a 16th century building using non-destructive techniques. The research has been developed by Letzai, Ruiz, Esteban, Prieto, Flores, and Gabriela Fernández from la Pontificia Universidad Católica, Madre, Maestra, and la Universidad Nacional, Pedro, Ureña, located in Santo Domingo, Dominican Republic. The structure of the presentation consists in an introduction, objective, case study, methodology, results, and conclusions. Early detection of damage associated with moisture buildup in brickwork, brick or stone masonry, concrete and wood elements helps prevent irreversible harm and may apply relevant data for the rehabilitation and preservation of historic buildings. Moisture can cause different lesions in the building. Some become harmful, such as fungi, that can cause health problems, or irreversible, such as rot. Therefore, it is very important once the lesion is detected to find out its origin to cure the root of the issue. Therefore, the objective of this study is to analyze the surface moisture conditions in a 16th century building located in the colonial city of Santo Domingo, Dominican Republic, by non-destructive techniques. The study building was one of the 16th century. It is located at 215 Arzobispo Meriño Street, 80 meters away from the Plaza of the Arms, today Parque Colón, and 150 meters from the Cathedral of Santo Domingo, Primada de América. That area of the city is the oldest part known as the city of Ovando. The building site is 720 square meters, and it is located on an east-west direction. The building is 2 stories, with a gallery, patio, and backyard. The walls are built with mixed materials. Some are stone and brick masonry, and others are rammed earth. The floors were originally brick, and today they are ceramic. It has 2-story gallery, with brick arches that join the 2 original bodies of the house. The mezzanine of the house was made of wood, and currently has a light concrete slab. The original roof was gabbled with wooden beams, mortar, and brick. Currently, the roof is gabbled with the same slope as the original roof, but it is made of lightweight concrete. In some mezzanines and ceilings of the house, old wooden beams are preserved. On the south side of the house, there is a dividing well that rises to the 2nd floor, being one of the only 2 wells of this type reported so far in the colonial city. The facade is simple, with a cornice at the top and a baseboard at the bottom. It has 9 doors and a continuous balcony with a metal railing on the 2nd level, a product of the modifications made to the building at the end of the 19th century. The following methodology has been used to develop this research: visual inspection, environmental conditions, infrared thermography, electrical resistance measuring. In relation to the visual inspection, moisture stains are observed on the facade on the 1st and 2nd levels. Under the balcony, there's a greenery and moss. In some areas, there is paint detachment, bulging in the plaster and some cracks. The upper cornice is broken in some places, and black crust is observed. On the interior walls of the 1st and 2nd levels, there are also large damp spots, bulging in the plaster, some cracks and paint peelings. In the main patio, dampness is observed by capillarity in the walls and columns. On the other hand, in some areas of the roof, humidity is observed due to the plugging of the downspouts, allowing the water infiltration, the appearance of the plants, and the development of black crust. Dominican Republic is located in the Caribbean, specifically in the northern latitude of the Tropic of Cancer, in a tropical climate zone where the temperature remains constant and generally humid almost all year around. In this slide, the data measured in situ on July 17th and 18th in 2019. In this case, there is an average of 80% relative humidity. Ambient temperatures are maintained in the range of 25 degrees Celsius and 34 degrees Celsius during the day and night, with few changes. Regarding infrared thermography, in the exterior facade, humidity is observed just in the balcony area, permitting the appearance of plants and the presence of humidity in the wall. At the beginning of the wall, some specific humidity can be observed due to the runoff of rainwater and humidity by capillarity, while in the second level, there is a presence of humidity on the cornice and in a large part of the wall. This is probably since the water collection channel is not in good condition, allowing the infiltration of water towards the facade. In the lower detailed thermal images, the humidity in the balcony area is observed, while in the upper detail, the humidity of the cornice and part of the walls are observed. In the interior facade, the first floor, it can be observed that there is humidity inside, just in the area of the mezzanine slab, due to the leaks that occur from the accumulated water on the balcony. In the case of the second level thermograms, humidity is observed at the level of the mezzanine slab, due to the infiltration of water from the balcony towards the interior, creating humidity by capillarity in the walls at this level. It is also observed that there is dampness in the corners of the facade, most likely generated by the breakage of the rainwater downspouts. Likewise, some dampness is detected in the upper part of the inferior facade, most likely due to the accumulation of water on the cornice or the breakage of the drains, allowing the infiltration of water towards the wall. In the main patio, in the thermograms, humidity can be observed throughout the cornice as a result of the accumulation of water and the growth of vegetation in a large part of the walls. Humidity from the roof to the ground in the areas where there are downspouts are located, due to their breakage, even allowing the presence of humidity in the mezzanine slab, dampness due to the capillarity at the start of the columns and the walls. In the corridor, first level, in the thermal images it can be observed that in the columns and the end of the corridor, humidity produced by the breakage of the damp spouts is present, generating humidity in both of the arches and in the slab of mezzanine. In addition, dampness is also produced in the arches due to the infiltration of rainwater that falls in the second level, permeating towards the slab and descending to them. On the other hand, it can be seen that there is moisture by capillarity at the base of the columns and on the walls in the inside of the corridor. The corridor of the second level, humidity from the roof of the mezzanine slab in the corner area because of the breakage of the rainwater downpipe and the growth of vegetation on the wall. Also, localized humidity is seen in the arch. It must be the product of water infiltration through the roof. And on the other hand, and at the start of the columns, there is dampness due to capillarity, due to the water that accumulates because of the rain. And in the columns at the end, also due to water infiltrations due to the breakage of the downspouts. In the interior wall, there is a point of humidity. This is due to the breakage of the bathroom water pipe that is inside of that space. On the roof, there is a hotter area than the others. This is probably due to the fact that just in that point there is a greater solar incidence, while the rest of the roof is shaded by trees. In the first floor, while in the thermograms, it can be observed that there is dampness by capillarity at the start of the wall in practically all the walls of the first level. Electrical resistant measurement. In Figure A, it illustrates a zone that is too humid, color blue, just as the beginning of the column produces by dampness due to capillarity. Likewise, it is observed that the humidity decreases towards the top of the column, having an intermediate area, color yellow, and then a sufficient dry humidity, color red. In Figure B, a significant humidity is shown in the map at the meeting between the wall and the arcade of the second level corridor, an overly humid area, more than 95. It is observed running from the roof to the mezzanine slab, opening up more and more as you get closer to the slab. Areas with the intermediate position are also present, from 85 to 95, and other zones that are sufficiently dry with humidity of 0 to 85. In Figure C, a small section in the exterior facade is observed, just below the balcony, where there is a zone that is too humid, in color blue, followed by the intermediate zone in color yellow, and finally a sufficiently dry humidity color red. To conclude, in the visual inspection, it is observed that there is a significant deterioration in the walls of the facade and the main patio, especially due to presence of humidity, permitting the appearance of plants and the development of black crust. The mezzanine slab, in general, is in good condition, with small exceptions, while the roofs are in good condition and do not present damp. The results obtained with the infrared thermography have allowed the detection of a series of humidity, which can be summarized as humidity by capillarity, humidity by water infiltration due to the breakage of the downspout or accumulation of water in the balcony and cornice area, in addition to the growth of vegetations on the wall. While the results of the electrical resistant measuring confirm the humidity found with the infrared thermography, indicating that there are very humid areas, other sufficiently dry, and intermediate area between these two. In conclusion, it can be said that the use of these two methods combined with visual inspection allows a precise and rapid detection of the humidity present in the construction elements of a historic building, thus contributing to its preservation. Thank you very much.